So we are back with the new topic related to the Siemens safety packages for HCPUs. Siemens safety package for HCPU is S7F FH systems. They are this package is working on HCPUs, and there are many different versions of HCPUs in Siemens portfolio. So it's a very detailed course tutorial, and you can check our website for more information. In this video, that is one of the final projects. We have a function block from ProSafe RS software safety system, ProSafe RS safety system, that is Yokogawa safety system. So we want to use this chart, the 2 out of 3 analog voting from Yokogawa. We want to use this chart and implement the same functionality by using block types, safety block types in CFC. We want to implement this the same functionality in Siemens CFC. There is an analog voter in the library, safety library from Siemens, but when you just simply compare the features, the voter from Siemens is not easy to master, and it's this table here. This table is a very easy for engineers to understand. Very practical table. If you have a 2 out of 3 application, safety application in industry, this block and this table is much easier to understand, easier to use compared to the same functionality from the safety library in S7F and FH library, Siemens library. So we want to implement the same function. So if you, we read more about this block, this is the layout for this function. We have 3 inputs that are the actual IO real in the ProSafe. It's a combination of a real data type plus status. So it's somehow similar to the concept in Siemens. In Siemens, we have the output of driver. We have the real output of the driver that is in real, and the status this is normally the qubit signal. So there is a there are some other there are other variables like the delay time. This is the delay time. This is the failsafe. And this is a difference value. DL is somehow like allowable range or allowable difference between these values and the median values. So for if the output in normal cases, if everything is normal, if everything is normal, the output will be the median value. So in this case, we calculate the absolute difference between each the output, the median, and the each input. So minus 2, it is difference 2, difference 3, absolute output minus input 3, absolute. So if, as an example, we have input 1 to be 22, 23, and 25, the output will be 23, difference 1 will be 1, difference 2 is 0 because input 2 is the output, and difference 3 will be 2. So very easily, so it's a somehow decision making how to select the output in different cases. So the main parameters are the quality of signals, and the what can I say, deviation from output. So based on the quality of signals and based on the deviation from output, we decide and we form the output. This table here is some area of the block. It's a very smart block, and it's smart, and the reason we selected this block to check is it's a good block. It's much better compared to the block, the voting block in Siemens library. So if the quality of all signals in the first case, if the quality of the signals are okay, so all signals are okay, quality of signals, so there is no Q-bad signal, and deviation is not an issue. If deviation is not an issue, the median of the input 1, input 2, and input 3 will be the output, and the status will be true. For this particular case, because this function is not final yet, we don't focus on these. We try to imitate as much as possible to generate these signals, but in order to be exactly the same, we need to do more tests and more modification, alteration to the code. So consider that the input 1 is 22, input 2 is 23, and input 3 is 25. And DEL, the range, consider DL is 10, as we will test that. So the difference is somehow 1 and 2, 1, 0, and 2, and we are in the permitted range. As an example, difference 3, we can just write that for difference 3 is equal to 2, because the difference between 25 and 23 is 2. It's so in this case, there is no problem. It's a normal situation. Everything is true, and the median 23 is the output. Everything is good. everybody is happy, and the output will be 23. Deviation will happen. Consider a normal case is in some burner management system for boiler application. You have impurities in the boiler system, impurity in water, and the level measurement may have some problem. One of the transmitters may deviate gradually from the rest. So consider that input 1 is deviating, and based on this, consider we have like 10, 23, and 25. Our big problem here is input 1. The difference for input 1 is getting difference 1 is getting 13, and it's not in this it's not fitting in this it's not fitting in this equation. So this is the deviation. At first we just ignore the condition, we just ignore the case for a time period. In our test it's around 20 seconds in order to do the simulation. So all conditions are like the normal case. In this situation we have the deviation, but we wait and see what will happen during this period of time. It's in our example 10 seconds. For 10 seconds we wait and see what will happen. So during this period of time we just report the median to the output 23, and everything is reported as normal. So it's similar to the first case. But when the 10 or 20, I should check the I think it's 20. Let me check. Yeah. Delay is 20 seconds. 20 seconds. So the delays, I just selected it to to exaggerate a bit more, and after the time delay is passed, let me return to the design board. So after the time delay is passed, we still report the median of input 1, input 2, and input 3, and we report the normal 1 signal as false. It's an indication of an error, but still we have 23 as the output. We have the 23 as the output. Again, in this case, in the next case, we don't try to solve the problem for level transmitter 1. So level transmitter 1 is still 10. Level transmitter 2 is reporting 23. And level transmitter 3 is reporting like 53. So we didn't solve the problem for transmitter 1, and we have a problem for another transmitter. 2 inputs are getting out of range. So if you calculate difference 3 is getting 20. And for sure it's out of range. In this case, we have two cases. First, we wait for 20 seconds, wait for 20 seconds. We generate the median value, that is 23. And consider that we have everything normal, but for now something happens and we report everything normal, the median is reported. And if after 20 seconds we just we couldn't make everything back to normal after two transmitters, after two failing transmitters, if we don't try to solve the issues after passing the delay time, we will report the failsafe value to the output. And in most of the cases, failsafe for temperature, normally we consider the high limit, and for level, I guess we can use most high and low. But if I had the chance to select the maximum 100% for level, I will select. And this will be a shutdown because we ignored two wrong or two transmitters with the deviation, and that's not good for operating a fail-safe loop. In a consider we use two out of three in critical processes in a boiler or in anywhere when there is a voting system. So all of those transmitters, we need to ensure that everything is working properly. If there is a slight deviation, it should be maintained to return to normal operation. And if we ignore, that's not this case is not real industrial case. It will not happen. There are some people that are monitoring the whole process, but as a safety programmer, you need to consider everything. If you can imagine that it may not happen in the real industrial application. So in the next part, we check the quality of the transmitters, and here we have one missing signal, input 1. The transmitter is faulty. Transmitter, possibly transmitter is dead or is out of range or everything. So this system reported via QBAT quality signal that input 1 is not good. So if input 1, we don't have input 1, so we check the input 2 and 3, the remaining good quality signals. And as an example, consider we have the input 1 that is not important for us, but still we have 22, 23, and 25. We ignore this bad quality signal here, and if the remaining signals, if the difference between these, the absolute difference is less than the permitted deviation, the absolute will be 2, and is within the range. If permitted deviation is 10%, so it's okay, and the median value of failsafe, input 2 and input 3. So failsafe is 100, input 2 sorry, 25 is input 3, input 2 is 23, and the median value will be 25. It will be reported. We report that the quality for normal 1 is false, but the rest we report they are true. So it's okay. We can, if we have one faulty signal, we can operate the process and we can solve the transfer failure and just report something is wrong here. But if we ignore again, what will happen? Consider in this case we have 22 input 1. Let me zoom a bit here. 22, 23, and like 43. So in this case we ignore input 1, that is not valid. Gain the deviation, the difference between the inputs, the good quality input is outside the range. Outside the range, that's 20% is not within the range, that is 10%. So this is the violation, and we move to the first part. In this section, consider the PLC is measuring the deviation is not within the range, so we wait for 20 seconds. Within the case, within this situation, if we are in this situation, we behave like this. This previous case here, the median value between 23, 25, and 100 will be reported as the median, and everything is normal. But what will happen if we ignore this case, and this case is the condition is more than 20 seconds, we will report the failsafe as the output, and this is a shutdown, and this is the shutdown. All binary signals false, and this is a shutdown. The final in final case we have 2 or more Q-byte signals. That's not acceptable. 2 or more, as an example, Q-byte 1 or 2, 2 or more Q-byte signals, and it's not acceptable for a 2 out of 3 voting function block to behave like that. So this is a simple, a bit messy, like I just add some notes here, but very helpful chart. We implemented this Yokogawa ProSafe RS Yokogawa voting block in Siemens safety software for HCPU. So I will move to the simulation environment in PC07-8, and we will do some function tests on this logic. So let me just exit this presentation board, and we move to the function block. So this is the function block that is implemented in the block types in the safety environment for HCPU. So the first case, these are the inputs, MD400, MD404, MD408, these are the inputs, and these 3 signals, M200, M201, and 2, these are the quality signals. We didn't want to do the actual hardware connection. So we just simulate everything, and this is the acknowledgement. M207 is the acknowledgement. So let us just start doing a simple function test. In this case, input 1 is 25, you can see input 2 is 23, input 3 is 22, and 23 as the median is reported to the output. So let us just start, and we just make something run here. Input 3, we change input 3 to 10. It's a deviation. It will create a huge deviation for difference 3. So difference 3 is 13, and as you may remember, the permitted deviation is 10, and each difference should be within the half of this. This is the deviation for signal 3, transfer 3. After 20 seconds, we have normal 3 is getting 0. Normal 3 is getting 0. But we don't, do a big change in the output. So 23 is still the median, but we will report that something is wrong. The deviation is not within the range. We can use the rest of the signals in order to generate a signal, an alarm that the deviation is not okay. So the next, so if you have one signal that deviation in one signal, we can ignore it. But when we have two signals, like 25, I change it to 45, and for a period of time it's okay. You can see difference 1 is huge. We wait for 20 seconds. The delay time you can adjust. When we have two deviations after this delay time, the output will be fail-safe. The output will be fail-safe, and it's a shutdown. After the shutdown, possibly we check everything and solve the problem in transmitters, and we return the machine into the normal operation. And still we have that 100, and we need to reset. So the block is getting back to normal. So in the next case, we simulate the bad quality signals from the table, the second half of the table. If we have one signal, the Q bad is active, one transmitter 1 is not good. So the value will be between 21, 23, and 100. Still 23 is the median, and we are okay. We will work with that. If it's in the real application, we should go and check the transmitter, solve the problem, and return everything to the normal. So input 1 is not considered in the calculation, and input 2 and 3, the difference is within the deviation limit. So consider that one of these signals are changing dramatically, as we have bad luck. 2 and 3, like 10. It's a huge difference. We can tolerate this problem for 20 seconds for this delay time. We have one bad quality signal. The other signal has a huge deviation, and after the delay time, if we cannot solve this problem, we have the shutdown here, and the failsafe will be in output after the delay time. So let me return everything to normal values, 22, remove the bad quality, and press acknowledge. And the final case, we need to, for final function tests, we have two bad quality signals. So as an example, consider input 3 and input 2. If we have two bad quality signals, shut down immediately, and everything is getting normal after the quality is returning to the normal case. So very simple program. The program is very simple, and the program is developed by the CFC programming language, and the functionality in this safety library that we have used is the block types. So if you want to see what how the program is developed, it's a complex block. In order to implement the whole functionality, we use the whole the table and different tools in the library in order to implement this simple functionality. So the course will be available very soon in our website. If you are interested into implementing some cool, very interesting safety algorithm by using the Siemens library, S7-F FH library for HCPUs, visit our website. Possibly at the end of the March it will be available. You can register and enroll the course, and explore the possibility, and I'm sure that you will enjoy. So I stop the video here, and we will share more topics here regarding to this course, and bye for now.